in this example, we have another limit to which we're going to use power series to evaluate that limit. So this time we have cosine, and then there's an interior composite function of x squared, e raised to the x to the fourth, so another interior composite function, and finally another composite x to the fourth for sine. Now, let's first of all remember that sine, cosine, and e have power series representations that are given to us. So these are the power series representations. And all we're going to do is we're just going to substitute back in for x for each of these. So if this were ex to the fourth, all I'm going to do is just plug in x to the fourth to the n. So this would be x to the fourth to the n. And this would be, since this would be sine x to the fourth, we would just plug in x to the fourth to the 2n plus 1. And then this was cos x squared. Then we're just going to plug in x squared to the 2n. And I'm just going to write these out below. Okay, so back here, cos of x squared is going to be equal to the series n equals 0 to infinity minus 1 to the n of x squared to the 2n divided by 2n factorial, right? And again, all I did was I just went up and I just replaced this x. So this x to the 2n, I just replaced this x with x squared. And then I'm going to do the same thing for the other two. I'm going to replace each of these with x to the fourth. All right, so for our e to the x to the fourth, that's going to be equal to series n equals 0 to infinity of x to the fourth to the n divided by n factorial, right? And then finally, we're going to have sine of x to the fourth, and that's going to be the series n equals 0 to infinity minus 1 to the n, x to the fourth to the 2n plus 1 divided by 2n plus 1 factorial. And then we're just going to write out some terms. Okay, so again, to write out the terms, you're going to plug in n equals 0, 1, 2, 3. Okay, and then maybe another 1 or 2 if we need it. Okay, so for instance, when we substitute 0 back in, this is just going to be 1. When we substitute, and again, we substitute 0 back in for all of these. All right, and then if we substitute a 1 back in, that's going to be a negative from here. We're going to have an x square square, so that's x to the fourth, and then this will be 2 factorial. And then finally, we're going to have an x, we're going to have a positive, we're going to have an x squared to the 2n, or x squared to the fourth, so that'll be x to the eighth divided by 4 factorial, and then minus x to the 12th over 6 factorial, and that's just going to keep going forever. Right. So again, just substituting 1, 2, 3, 4 back into this expression right here to expand it. Now we're going to do the same thing here. So if I substitute 0 back in, I get 1. If I substitute 1 back in, that's going to be plus x to the fourth over 1 factorial. And then if I substitute 2 back in, all right, so substituting 2 back in, that's going to be x to the eighth divided by 2 fact, and then x to the 12th divided by 3 fact, and that's going to keep going on infinitesimally. And then finally down here, if I substitute 0 back in, all right, so this is going to become x to the fourth. And then if I substitute a 1 back in, that's going to be minus, if I substitute 1 back in, this becomes x to the fourth cubed. So that's going to be x to the 12th divided by 3 factorial. And then if I substitute a 2 back in, it's going to be a positive, and then an x to the fourth to the fifth, which is x to the 20th over 5 factorial, and then x to the 28th divided by 7 factorial. And then that's just going to keep going on forever. All right, now that we have these set up, we can substitute back in to the original series for each of these. Okay, so now we're going to get the limit as n approaches infinity And again, I'm going to start by substituting for cos squared. So n approaches infinity. And when we substitute for cos square, right, this is going to be 1 minus x to the fourth over 2, since 2 factorial is 2, plus x to the eighth over 24, minus x to the 12th over 6 factorial is going to be 720. All right, and then that just keeps going on forever. Minus e to the fourth. So that's going to be these terms right here. So that's going to be 1 x to the fourth over 1, and then x to the eighth over 2, x to the 12th over 6, and that's just going to keep going on forever. And then finally in the denominator, we're going to have this series right here. So that's, or these terms, and then infinitesimally it's going to go on. So we have x to the fourth minus x to the 12th divided by 6, since 3 factorial is 6. Right. And then plus x to the 20th over 120. So that's 5 factorial minus x to the 28th over 40, because that's 7 factorial, and then going on forever. All right, so some good news. We have a 1 minus 1. So those are going to cancel out. And then I noticed that x to the fourth is the highest power in the denominator. And then also the lowest power in the denominator in this case, and x to the fourth is the lowest power in the numerator. So let's factor that out. Okay, maybe we can cancel some stuff out. So this is going to be the limit as x approaches infinity. Sorry, this should be an x, not an n, just so you use series tests. And so we're going to have a negative x to the fourth over 2 plus x to the eighth over 24 minus x to the 12th. Oh, I'm sorry, we meant to factor out that x to the fourth. So let's do that. All right, so we're going to have an x to the fourth on the outside of all of this. Okay, that's going to be a half, and then an x to the fourth factoring from here, and then an x to the eighth over 720. All right, and then that's just going to go on forever. Now we're also going to distribute this negative to all the terms. Okay, so if there's a coefficient, we have to make sure we distribute. So that's going to be minus 1 minus x to the fourth over 2 minus x to the eighth over 6. And then that's going to go on forever. All right, so again, just factoring from here, here, here. All right. Finally, I'm going to factor in x to the fourth from the denominator. That's going to leave me with 1 minus x to the eighth over 6 plus x to the 16th over 120 minus x to the 24th over 40 plus infinitesimal. All right, so some good news. X to the fourths are going to cancel. We can add these two terms together. And so our limit as x approaches 0, not infinity, and it should be 0 as well here. So sorry about that. That was just the original problem. Limit as x approaches 0. All right, so we can't just change that. Just a copy error. Not going to affect the outcome. And so what's going to happen is that we're just going to combine. All right, and we get the limit as x approaches 0 of, this is going to be a minus 3 halves from this term and this term. And then we have x to the fourth over 24, x to the eighth over 720. And then we have a minus x to the fourth over 2, and then x to the eighth over 6. And that's just going to keep going on forever. Right. And then in the denominator, we have 1 minus x to the eighth over 6 plus x to the 16th over 720 minus x to the 24th over 40. All right, so finally, we can substitute 0 back in. And notice when we substitute 0 back in, all of the terms that have an x in them, and that's going to be all the terms thereafter, okay, because they're higher degree than 4, and the numerator and denominator are going to cancel out. We're left with negative 3 halves over 1, which is negative 3 halves. All right, this is a really cool example because this would be a very difficult limit to evaluate without the series. All right. So this is one where a series is really helpful for us because, as you can see, if we were to take L'Hopital's rule, we might never get to indeterminate form that's going to be helpful to us. All right. Or if we did, the derivatives might be pretty ugly because we would have some product rules eventually. All right. So that's how we can use our series to be able to evaluate limits. In the next section, we're going to see how to use series to be able to evaluate definite intervals, or at least approximate them.